Okay, everybody, we're going to get underway here. So this evening, we're going to wrap up a few ideas in chapter 2 and then get started on the first half of chapter 3. So last time we reached the uh, point of the chapter right at the bottom, I would say in 2.8, 2.9, where we were looking at naming of different ionic compounds and how to name different molecular ones. So I'm going to begin. I want to get some information from you. So last week when we had a poll, many students said they were not entirely confident with their skill when it came to dimensional analysis. So in an email, I was able to share a worksheet and a key with y'all. So I'm curious when it comes to, I'd say that particular resource, what best describes your perspective? And when I say what best describes your perspective, what did you do with that information? So let me give you your choices. Take a second, read them, and then I'll shoot you a poll. So when it comes to that particular worksheet, help me out. Would you say you don't remember receiving the email? Would it be that you are aware of that resource, but you've chosen not to use it, even though you think it could be helpful? You've completed some of it, or you're already very confident with that skill, so you don't think you need an additional resource? Help me out. This will help me better understand how to share resources with you. Take about 10 more seconds, please. Okay, share results with y'all. We have pretty big distribution, which is fine. About a quarter of the class say that you don't remember having received that, which is fine. I know a lot of information is sent to you in different ways. Um, this tells me though, I might end up resending that within an email. So if you see that, I'm not trying to bother you again, but if we got about a quarter of the class unaware of that as a particular resource, I don't want it hidden from you all in some way. Um, what we're working on this evening, then, we're going to begin by wrapping up the ideas here at the end of chapter 2. So one thing that we were working on last time when it came to molecular and ionic compounds, we were trying to make connections between the formula that we'd have, what was taking place at the particle level, and the name. And what we're going to do when we wrap up the idea here in just a moment, we're going to find that when we're naming these different substances, it first begins with having the correct classification. I think we have 4 different categories that are described in the book when it comes to classify these. We had ionic compounds. They have a particular naming scheme. These binary molecular ones, that's something we talked a little bit about last time. They have a naming approach. And then we're going to see 2 new classifications, acids and organic molecules. So I'm of the mind, before we can name something, we've got to be able to put it into the correct category. Putting things in terms of either whether were they ionic or molecular, that's something we worked on last time. We worked on it last time and we saw how it led to different arrangements. When we were seeing molecular ones, for example, we would be expecting discrete, distinct molecules. When we were looking at ionic compounds, no molecules, we just had this extended solid that kept going and going, and we'd be using empirical formulas to communicate uh, the ratio of the atoms that were present. We looked at naming of the ionic compounds: sodium chloride, magnesium bromide, aluminum oxide, iron 3 oxide. That's how I would be naming those ionic compounds. When it came to molecular ones, these binary molecular, carbon dioxide was an example of how we would name that. That was the one where we had the different prefixes, carbon dioxide. Now, if I were to use that same scheme for H2O, I think it's appropriate. I think it would be dihydrogen oxide or dihydrogen monoxide. Either way, we don't really use that, right? We just call it water. Many times we're going to see that there are different common names. So even though we're trying to learn this particular naming scheme, it's not like that's entirely how it's always used. Now, if I look within the molecular ones here, a couple other examples. CH3COOH, that's going to be named as an acid. So that's going to be a different naming approach. C2H6, that's an example of an organic molecule that has a different naming approach. Let me show you what I mean within that. Now, last time when we were looking at the structural comparisons, I thought people did a really good job of saying this was an ionic compound and this one was molecular. We had an example of an ionic solid and a molecular gas. And I also added to that the idea that you could be a molecular substance and also a solid, but a difference there would be how I see these spaces between the molecules. Whereas an ionic compound, it seems far more continuous as they're right next to each other. This led us to this final question. This is where we left last time. So we had, this question is from the end of the chapter. It says the following represents an ionic compound and the blue spheres are cations and the red spheres are anions. Which would be consistent with this? So when I look at that particular image, what I'm taking away is, well, it's an ionic compound and it has a 2-to-1 ratio for the cations to the anions. 2 cations for every 1 anion. So if I began to look at the different choices, what would it mean to narrow this down to the correct answer? Well, if I look at KBr, potassium bromide, I would say that's an ionic compound, but it's in a 1-to-1 ratio. So the ratio is not correct. Iron 3 sulfate, ionic compound, I like it, but it's in a 2-to-3 cation to anion ratio. So that's not correct. Calcium nitrate, in that example, I'd have to write the actual formula. And I would see that I have 1 cation for every 2 anions. In order to write this, I have to know that nitrate is NO3 minus, and calcium is in the +2 column as an alkaline earth. That leads me to the formula. That's not correct either. I think the best example, the best answer within this is the potassium sulfate. Ionic compound in a 2-to-1 ratio of 2 cations for every 1 anion. I think that's the best choice here. Now, sometimes students would say, well, what about H2S? That seems like it's 2-to-1. That one we have to be a little bit careful with. Because if I find hydrogen and sulfur, those are both nonmetals. I think H2S forms a molecule. It is not forming an ionic compound. In this class, I think hydrogen is only going to be found in molecules for us. When we have examples of ionic compounds, we really want to be looking for different metal cations, or I guess another example would be our ammonium cation. That would be an example, NH4 plus, of a molecule that's also a cation. Looking a little bit then at the remaining categories of classifications. When it comes to acids, let's start by knowing the small group here of acids. These are also comprised only of nonmetals. These are common acids that we're going to see a lot in this course. So let's begin our understanding by having memorized the common ones. What I'd like you to do is to memorize the name and the formula for nitric acid, sulfuric acid, acetic acid, phosphoric acid, and hydrochloric acid. We may expand a little bit beyond that, but know the name and formula for these. You're already working to memorize polyatomic anions, polyatomic cations. Add this to the list of what I'd like you to memorize. Now, if you look at this, some of these acids include polyatomic anions that we're already supposed to know. They fit together. And what I mean by that, look at the formulas here. Nitric acid includes the nitrate anion. Sulfuric acid, the sulfate anion. Acetic acid, the acetate. Phosphoric acid, the phosphate. So this really fits together and helps within our memorization scheme. If you know the charge for the polyatomic anion, you know the number of hydrogen atoms that you have attached there for the acid. Nitrate is NO3 minus, oops, sorry about that, NO3 minus. It has 1 hydrogen added to it. Sulfate, SO4 2 minus, so it has 2 hydrogens. Acetate is -1, so it has 1 hydrogen. Phosphoric acid, phosphate is PO4 3-, so it has 3 hydrogens. So by memorizing the formula for the polyatomic and the charge, you're really at the same time in a great spot to begin to memorize these acids. Now, I've mentioned how these include within the molecule these polyatomic anions, but let's be careful with this. The acids that I see listed here, they exist as molecules. They are not ionic compounds. There are distinct, discrete molecules. We look, for example, as acetic acid as an example of a molecule. And sure enough, it is. So even though we are saying it helps to make sense of this when we think about the polyatomic anions, let's recognize that these are consisting entirely of nonmetals. These are molecules. These are not ionic compounds. The last classification, and we're going to look just really briefly at this, are a few simple organic molecules. These are discussed right at the end of chapter 2. Let me show you the naming scheme for this. So first of all, if I'm just looking at the patterns for how these are drawn, they look really similar. I see a carbon atom that has 4 different neighbors around it. That's what those lines are designating, single bonds. I see 2 carbons, and all the way around it are hydrogen. I see 3 carbons, all the way around it are hydrogen. These are examples of what are called alkanes, where you're changing the number of carbon atoms. When you have 1 carbon atom, it's methane, 2 ethane, 3 propane. Notice they all have an ANE ending on it. The prefix that you see for that ANE tells you how many carbons you have. Methane has 1 carbon, ethane has 2, propane has 3. If you were to have 4 right there, you would simply see what is the prefix, and that would be butane. Take a second, see if you can make sense of this next one. It sure seems like it's extending the pattern, and I see 1, 2, 3, 4, 5 carbons, so that would be pentane. I think several of these organic molecules are ones that you've heard of before. My hunch is you've probably heard of octane when you think about components in your gasoline, and perhaps hexane as well. So let's be able to be familiar with this naming scheme for these simple organic molecules, and also make just one additional change to it. What if instead of having the hydrogen on the side, it had an OH group instead? If you change that to an OH group, instead of being called an alkane, now it's called an alcohol. I'm sure you've heard of alcohols as a substance, chemical substance. Notice the only difference is instead of having this ane ending on it, we end up with an OL ending. Methanol, ethanol, propanol, those are also ones that I think you'd be able to sketch, interpret, identify. So we can use the same scheme here with the prefixes. You could have butanol, you can have hexanol, same kind of plan within that. That's all we're going to do in this class with organic molecules. But let's add that as another classification scheme. So I give a few suggestion problems that ask you to apply naming. Notice how they're being put together. Here's a whole grouping involving ionic compounds. Here's binary molecular ones. Here's another look at ionic. These are all ones, if you want to practice some naming, I think you can do well with these. Now, as we move from chapter 2 to chapter 3, got another question for you. So as I've mentioned several times, I'm a chemical education researcher. That's what I work on. And for the last 6 years, I've really improved my own understanding for what are called evidence-based learning strategies. What are the best ways to learn? What do cognitive scientists tell us? Now, I'm sure that this information is going to help you in this class, because who wouldn't want to be a better learner? So what I did was I made a video and I put it in perusal. So I was going to ask this as a question. Should the video and perusal be listed for credit? Should it be optional? Or should I make it extra credit? Tell me in the chat what you think. Now, as those are rolling in right there, no surprise, who wouldn't choose extra credit? Okay, so I'm going to set it up within Perusal for extra credit. Now, so I'll send you out an update when that's posted. Should be able to post it tomorrow. Let me ask you a different polling question though. I'll have it listed for extra credit, but what I'm curious is this. What are you going to do with the video? Are you going to engage with the video and treat it like an assignment where you respond to questions, you add your own comments and the like? How are you going to use the video? Because I know depending on how you use the video, it's going to affect how much you learn from it. What will be your strategy with the video? In many ways, this could be the most important video all semester because I think it has some really powerful ideas. Take about 10 more seconds. So the response I'm seeing with this is what I would expect. I'm seeing a lot of indication here that you're going to try to learn from it, treating it as an assignment. I think that's an outstanding strategy. So I'll post that. I'll shoot everybody a message. So it's going to be listed within Perusal. And I'll try to make clear that it's listed as something that's going to provide you extra credit within the Perusal system. So I'll be posting that probably this evening. So look for an update on that, please. Let's move on now to ideas within chapter 3. So within chapter 3, this has certainly a lot of chemistry to it. And when I say a lot of chemistry, well, what have we been doing so far? People have been making comments, let's say when we were looking at the experiments of Thomson, Millikan, and Rutherford, but well, this seems like a lot of physics. I agree, those are all physicists. Those are folks that won Nobel Prizes. Rutherford won in chemistry, but the other ones, those are all physicists. So I agree with you. The ideas that we're getting here though in chapter 3, this is really to the core, obviously chemistry stuff. So I think we have an opportunity to begin discussing this. We're going to look at chapter 3 both this week and then also a little bit into next week as well. So what I grabbed right here, these are some very typical questions that you'll find in chapter 3. So when I list these right here, one thing that's helpful is at the start, ask yourself the question, well, can you solve questions like this already? And if you can't, well, what kinds of skills or ideas does appear that you might need? So when I grab these right here, I think these are related to some of the ideas that we've already been talking about. I see the word empirical formula. That's something we've been discussing. I see formulas like NH3. I see formulas like C3H8. Okay, that looks like a hydrocarbon, a simple organic that we just talked about. And in fact, that would be one that I think we're developing the skill that we can now name. C3H8, 3 carbons, total of 8 hydrogens around it. The prefix is propane when I have 3 of them. We've discussed a little bit how O2 is a diatomic molecule, oxygen gas. So we have some insights, I think, already within ideas from chapter 3. But it's also telling me we can't just look at the chapters independently. We're going to have to use the ideas in one section and see how that supports ideas in another. Now, as far as some new ideas within here, this idea of what will we do when we have information about the percentage of the mass of one of the elements? We haven't worked on that yet, but we're going to in chapter 3. This idea of connecting how many atoms you would have with how much they weigh, that's an idea that we're going to have to see and learn about in chapter 3. Other things, I see this word combusts. That's a reaction type that we're going to look at tonight. This idea of having a reaction and asking how much of something can be produced or what remains unreacted, that's involved in the topic of stoichiometry. Really an important idea in chapter 3. Also the symbolism here of MOL for a mole. All new ideas that we're going to have here that we're going to begin to explore tonight. So here's our pathway through the different ideas. And like I said, it's going to take us a couple classes to get through the different parts in chapter 3. This progression that I have right here, this matches exactly the progression in the textbook. When I look at in my own analysis of these questions, if you remember, are the topics. The ones at the bottom are the ones students usually have a lot of success with, and the ones at the top are more difficult. And I'm putting in bold here if it's an important idea or skill for us. Extremely important in this class is being able to do stoichiometry problems. And there are many different examples. On your test, if I were to estimate, probably, I don't know, 20% of the exam is probably related to stoichiometry for your first test. So I want to make sure we have enough time that we can practice that over several different classes. Now, within the pre-class video, there was one pre-class video that was looking at aspects of chemical equations. I think that touches on part of the stoichiometry, which are when stoichiometry is related to particle representations. I think that those topics are also related to how do we write a balanced equation from a word description and the balancing itself. So within perusal, I thought people had some really good comments and it was helpful when we were looking at what is being described in a chemical equation. This idea that we could look at a particle level representation for hydrogen molecules, oxygen molecules to form H2O molecules. How we have this arrow designating when we go from the reactants to the products, and then also the formula that goes with it. Now within the formula, we want to be very careful. We have both coefficients that are in front, and we have subscripts that are shown below there. We need to be careful and recognize what both of those are communicating. So here's one of the responses I saw in perusal. It says the coefficient of 2 means that there are 2 H2O molecules in the product. The subscript of 2 means that there are 2 hydrogen atoms in each molecule of water. I really like that second sentence. The subscript of 2 means there are 2 hydrogen atoms in each molecule of water. So the subscript is telling me something about what's, in this case, within the molecule. I like that. But I think we need to be careful with the coefficient. The coefficients to me are telling me a proportion. It's telling me that when I have 2 molecules of H2 reacting with 1 molecule of H2, then I'll get 2 molecules of H2O. It's putting into words what this particle level description is telling me. So I agree that I'm going to get 2 H2O molecules, and that will match up when I have 2 and 1. So we got to be careful though with both of these parts. Let me show you what I mean within this. So I had this question within perusal, and I was really benefiting from your insights. So first of all, one thing is when we see these different coefficients, the 2, the 1, and the 2, many times you'll see it written where there is not a coefficient if it's supposed to designate a 1. So I could have a 1 there. If you don't see anything, it means that there is a 1 there. That's one thought to have in mind. Second is you'll see a lot of questions looking at these particle level reactions like this, where it'll say, here's what's initially in the container, and here's what's in the container after the reaction takes place. So they're trying to show a box before and a box after. I mean, it's not like there's a left and the right. It's just showing this is what the box looked like before, and this is what it looks like afterwards. This idea of, do you understand the scenario? A couple things that I would be understanding of this. If it tells me that it is a sealed container, if it's a sealed container, then I can't be adding or removing particles. If it's a sealed container, I got to make sure that I am not adding or removing molecules. And it appears okay. Meaning I see the same, I get 2 red particles, 2 red particles. 4 silver, 4 silver. That's what takes place in these scenarios. Now, this question right here I found was very insightful for me based on how you were seeing it. I asked, are these 2 describing the same chemical reaction? Would they have the same chemical equation? In which ways are they similar or different? There's a pretty clear consensus with this particular view. It says it looks like both the initial to final are describing the same reaction. They start with separate elements that chemically combine to form H2O in both situations. I like that. Because the quantity is greater in the second example, it would have a higher coefficient. I'm less clear about that last sentence there. Here was another one. The reaction is the same, but the quantity of reactant and product is different. They would have different chemical equations because the coefficients in front of the hydrogen and oxygen would be a greater number in the second example. I like the idea that these are both describing this reaction of hydrogen gas plus oxygen gas to give me H2O molecules. But I need you to think about what these coefficients mean differently. Consider this. Let's say I had a whole bunch of hydrogen molecules and oxygen molecules. This is another scenario. It's the same reaction once again. What would be the coefficients in this case? Is it still 2, 1, and 2, or do you need to adapt that to give you yet another scenario, another circumstance? I think it's always going to be the same coefficients. This is how I need you to think about it. The balanced equation is like a recipe. It tells you the proportions, the ratios for how the reactants combine and the products combine, how the reactants combine and the products are formed, excuse me. It's telling you the simplest way, the simplest ratio for how those can be combined. The coefficients are not telling you what is in the container. So we don't want to change the coefficients in a balanced equation when the amounts change. We're going to need to account for that in a different way, and we will. But we want to keep it so that the equation is telling us the simplest manner in which they're combining. The coefficients are describing those proportions. They're not telling us what is literally present in the container. So this idea, if you change the amounts, let's change the coefficients, we don't want to do that. We just want to have the simplest expression for it, the simplest recipe. Let me show you a little bit as far as what I mean. So let's say we're making sandwiches here. At the top, we have listed our recipe. We can have different amounts of bread, meat, and cheese and make sandwiches along the way. I can change the different resources, the different reactants that I have. And depending on the proportions I have, I'm making different numbers of sandwiches. But notice way at the top, I'm never changing my recipe. My recipe is always staying the same, even if I change the number of reactants. We will end up using that information, but we're not going to change the coefficients that we have within our recipe. Now, when I had this as a scenario right here, I asked, was this describing the same reaction? Would it have the same chemical equation? If not, what would be appropriate? I thought this was a pretty complete response. It says, no, this is not describing the same reaction. Now, this bottom particle diagram is representing the reaction between 2 molecules of hydrogen gas and 2 molecules of oxygen gas to form 2 molecules of H2O2, which is called hydrogen peroxide. This is not the same chemical equation as that to form water, and they propose that the correct one should be H2 plus O2 to give me H2O2. Let me ask you about that. Do you think that that is the correct expression? Or should the coefficients match what you see in the picture? Or do you have some other idea on that? Let me send you a polling question on that one. Do you agree with A, B, or C? Take about 10 more seconds. Okay. So as far as the consensus here, about half the class is saying that A would be the correct expression. And we're right at 50% on that. And 50% are saying, no, it should be either B or you might have a different idea. Now, I think A is telling us the simplest way that I can have hydrogen gas combined with oxygen gas to make H2O2. I think it is balanced in terms of the number of atoms that I have on hydrogen on each side and oxygen on each side. I think it's also showing me the correct molecules that would be involved. How I can have hydrogen react with oxygen to give me the H2O2. If you said A within that, I agree with you for that 50%. I think that is telling me the simplest proportions that I can use to combine to come up with the H2O2 that would be true to that particle representation. If you look at B and say, well, wait a minute, when I look at B, I see two hydrogen molecules. I see two oxygen molecules. I see two of the hydrogen peroxide. Shouldn't that be right? I think you're falling into the trap again of you're trying to make the equation tell you literally what is there in the container. The equation is telling us the simplest recipe. It doesn't have to tell us literally what is in the container. We will end up using that information, but we can keep the simplest recipe instead. We don't need to change the coefficients to make that happen. I'm going to double back just to our sandwich recipe here. At the top, here's my simplest recipe for making a sandwich. I can change the amount of reactants that I have and make sandwiches without ever changing what my recipe is. I can keep the same chemical reaction there at the top. It will work when I have a small number of reactants. And when I progressively increase the number of reactants that I have, I can keep the same recipe. I don't need to change the recipe when I change the number of reactants. Now, you might be saying, yeah, but how do you then figure out how many products that you form? How do you actually make that work? We're going to learn how to do that in chapter 3. But for now, let's have our lesson be, we are looking at a balanced chemical equation as our simplest recipe that we need to turn the reactants into the products. And the coefficients are showing us the proportions for those along the way. Let's look at this example right here when we're looking to see how things combine. This is one, instead of looking at sandwiches, where we have a balanced chemical equation. Nitrogen gas and hydrogen gas to form NH3. This is one where I asked, well, what would this look like as a particle level description? This is one where students actually submitted a drawing here. They even color coded. I guess the iPad came through for you on that, where they're showing nitrogen gas and hydrogen gas to form NH3. At this point, we don't need to know exactly how they're arranged in these molecules. Chapters 8 and 9, we're going to learn a lot about that. For now, we just want to make sure we have the right number of particles grouped together. Let's look at this one. So here I showed the reaction. Nitrogen gas and hydrogen gas to form NH3. I keep calling these nitrogen gas, hydrogen gas, because when they're found as the element, as a gas, it's a diatomic molecule. That's why I see N2 and H2. So let's say this is what I had in the container beforehand. What would be in the container afterwards? Can you use the balanced equation to see what you'll end up with at the particle level afterwards? I see that I have some N2 present. I've got H2 present, so I have the reactants, and I'm forming NH3 as the product. So you might say, well, let me put the NH3 in there. Let me put NH3 into the container as the final one. Would this be correct? Well, what we have to be careful with is it says it is a sealed container. If it's a sealed container, I can't add or lose particles. If I look over here, I see a total of 6 blue ones. I've got to have a total of 6 blue ones. I see a total of 6 gray ones. I've got to have a total of 6 gray ones. On these questions where it's taking place in a reactions in a sealed container, that's one thing that I need you to look out for. Now, if I look within the details here, it says that I'm forming NH3, and that's what's being drawn here. This coefficient here, this is telling me just part of the recipe. We need to be careful on that part too. When I say we need to be careful, we won't always just form 2 of these here. Remember, this coefficient is not telling us literally what is in the container. It's just telling us the simplest ratio in which they combine. This idea here of seeing what do we have before and what do we have after, as a learning objective, this is looking at the reaction stoichiometry, how the reactants combine to form the products, and a particle level description. That's something that we're going to continue to practice here within chapter 3. I wanted to introduce the idea tonight, but it's something we're going to continue to practice. If I look at that same one here within this PhET simulation, I could have the same chemical formula in a case where, okay, I don't have enough reactants to form any products. I could have exactly the right number to form the products. I could make it where I had leftover N2. I could make it where I have more than just 2 NH3s. My point being, once again, I'm keeping the chemical reaction the same, but by varying the amounts of the reactants, it changes what ends up in the container afterwards. So that's something that we'll be practicing when we work on stoichiometry. Another idea I had within the pre-class video was this one. So I put this in the category of trying to go from a word description to a balanced reaction. Calcium metal reacts with oxygen gas to produce solid calcium oxide. People had some really good questions as far as where they were getting stuck on this. So let me see if I can help out a couple of those. This would be my answer. How do I end up getting my answer? Couple things that I would be looking for. So first of all, when I have this balanced chemical equation, when I was also asking to identify any molecular compounds, that's my bad on that. I wasn't trying to make it trickier or anything. I wasn't trying to say, aha, O2 is a molecule, but not a compound. My mistake for trying to, if I confused you on that one. Now, as far as going from this then to try to figure out how did I get this balanced equation? So here was a question the student had. Are you able to distinguish because that it's O2 because it's written as oxygen gas and not like oxygen atom? Is there some basic way to like that to distinguish between the oxygen atom and the O2 in a word problem like this one? Excellent question. A lot of students had that. How do you know that it's listed as O2 as a reactant? I'm looking for exactly what that student brought up. If it says oxygen gas, that is when I'm going to write it as O2. If it says, if for those other diatomics, if you tell me hydrogen gas, I will write H2. Nitrogen gas, N2. Oxygen gas, O2. Fluorine gas, F2. Chlorine gas, Cl2. Any of those gases that I'm looking at, any of those elements, when it tells me that it is as a gas, it's going to be as the diatomic molecule. Let's have that as a skill for us. Second here, it says it's producing solid calcium oxide. This student's comment, I'm confused why the CaO wouldn't be a molecule too. What's going on with that one? Isn't it an ionic compound and a molecule? What's going on within that one? When I read calcium oxide, I'm thinking entirely an ionic compound. I'm thinking it's an ionic compound with calcium 2 plus and oxide 2 minus is the anion. I have subscripts just of 1 and 1 in the empirical formula because they combine 1 and 1. When I read calcium oxide, that's what's coming to mind. So I think that crucially within here, the first steps, if you want to come up with the equation, you would have to read that oxygen gas should be O2. Calcium oxide is an ionic compound that has this formula. And calcium metal, that's just an elemental form of calcium, calcium solid. That's what you'll then use to come up with the balance coefficients. It all begins with having the correct substances listed that you'll then try to balance. This is a case of taking an idea at the start of chapter 3, which is balancing reactions, and connecting it to an idea at the end of chapter 2, which is the naming. I'm really confident that that's a very typical exam question. This idea of the ionic compound, calcium oxide, definitely an ionic compound. There's not a discrete molecule. It's this alternating pattern of cations, anions throughout. Now, I've mentioned balancing chemical equations. When you have this on a test, I would say typically we have maybe one exam question on your first exam where the purpose of it is really just about balancing the equation. When we have questions like that, a lot of time the format is what you see at the top here, where we ask you to balance it, and then we ask for the sum of the coefficients. The reason we're asking that is we don't want to give you 4 choices and you check all of them. We want you to go through the process and then tell me something about it. And usually what we'll have you tell us about is add up all the coefficients for the whole thing, or add up all the coefficients for the reactants, or add up all the coefficients for the products, something like that. We don't want to give you different ones that you check. We want you to go through the process of balancing it and then tell us something about it. So within this first one right here, I think this is a very involved balancing of a chemical reaction. Let me share with you my strategy on this, okay? This isn't the easiest for me to communicate within slides, but let me show you what my reasoning is and see if you can follow through. If I'm balancing something like this where there's a lot going on, my strategy is going to be is if I see something that is independent, I'm going to balance it last. And by independent, when I look at something like O2 or N2, they're not in compound with other atoms. So I can always change their coefficient without worrying about changing another element at the same time. If I have that, I'm going to keep that for the last things that I balance because I can always make an adjustment and make those work. So that's one tip for you. If you have a complex one that you're balancing, if you have something that's independent, try to save that for last. So let's start to just go through the process. So right here, I'm going to balance this reaction first, and I'm going to be looking at the carbon in it. I'm just starting there. If I look at this, I see that I have 2 carbon atoms listed. So I'd have to put a 2 as the coefficient there. That's the only spot that I see carbon. So I know that my carbons are now working out. How about the next one? There's a total of 7 hydrogens here. Hydrogens only showing up over here. Now, if I pause within this, I see that I have 7 hydrogens, and over here it's going to be in multiples of 2. I've sort of run into trouble there because I can't multiply something by 2 and make it equal 7. Math doesn't work that way. My philosophy here is that odd numbers can mess around with you. When I have an odd number like 7, that's posing a difficulty for me. So I'm going to try to adjust that. Instead of having it set up with 7 hydrogens, I'm just going to double this and make this 2 and make that 4. And now I'll have an easier time of trying to balance the hydrogens. Because now I see I have a total of 7 times 2, which is 14. 7 times 2 is 14. This strategy of, well, if you have an odd number and it's messing with you, you can just double everything and that will get rid of that issue. How about if I now try to balance the nitrogens? I see that I have now a total of 2 nitrogens. So I could put a 1 there. Okay, I'm almost done. But this one's going to mess with us one more time. Because look right here. If I add up all of the oxygens on this side, I get to 15. That's an odd number. Odd numbers can mess with you. There's no way I can multiply something by 2 with whole numbers and get to 15. It would be possible. I could multiply it by 15 halves. Nothing wrong with that. That's another way to get to the number 15. And then I can multiply everything through to get rid of that fraction. That's one strategy that you can use. If you do that, 15 halves becomes 15, 2 becomes 4, 4 becomes 8, everything doubled throughout. So that's another way that you can deal with this idea when you have an odd number. Now, I was noticing within Perusal, a lot of people were doing a really good job coming up with the total for this. You weren't showing me your strategy, but I was seeing a lot of really good answers where you were able to answer that first one correctly. That first one right there, I think that's one of the most difficult ones that you would have on an exam when it comes to balancing an equation. And again, it comes back to this idea, if odd numbers are going to mess with you, you can always double everything that you have, and that gets rid of dealing with that odd number at that point. Leads to the same answer. Now, different type of question that I've seen on tests is a word description. What is the sum of the coefficients in the balance equation when aluminum hydroxide reacts with sulfuric acid to produce aluminum sulfate and water? Crucial within this one, we've got to be able to write what the equation is. As a student commented, well, where should we even start within this one? They were able to write the equation and then seem lost. This would be the equation I'd be starting with. Aluminum hydroxide, aluminum is 3 plus, it's in the +3 column. Hydroxide is OH minus. So this would be my formula for aluminum hydroxide. Sulfuric acid, that's an acid I've memorized. Aluminum sulfate, aluminum is +3. Sulfate is -2, so these would be the subscripts I would need. And then I have water present. This one right here, it seems like, yeah, there's a lot of chemistry there. These are all different things that we want to be able to name based on ideas in chapter 2. I see that there are polyatomics that I need to have memorized. I need to have memorized the formula, name and charge for hydroxide and for sulfate. And from there, I'm just going to see what does it mean to balance it. I have over here on the left-hand side an aluminum. Over here, I have 2 of them. I need a value of 1 and a value of 2 then. I could now look to balance the sulfur, or in that case, I could balance the entire sulfate. That gets me a value of 3. And now finally, I can look to see balancing the water. I could add it up and say as a reactants, I've got a total of 18 oxygens. Right now I have 12 oxygens. So I need 6 more and that will balance it out. If you want to double check, you could add up to make sure it works for hydrogen too. The format on this one, really typical exam question. I'm really confident we've asked this before on a test as I look at it. What is the sum of the coefficients? And then you have this word description. This is telling me we really need to continue to improve our proficiency with the naming that we have in chapter 2, because we don't want to reach a point where maybe we're good at doing a balanced equation, but we're getting stuck because we don't know how to write the names for the different reactants and products. So we've talked a little bit here about balancing reactions. Great job paying attention so far. We're going to next look at a few examples here involving specific chemical reactions. And in particular, we're going to be looking and spending some time with what are called combustion reactions. Let's get through this idea right here, and then we'll give you a little mental break, okay? So when it comes to different reaction types, the main one that I need you to memorize is what's called a combustion reaction. In a combustion reaction, a hydrocarbon reacts with oxygen gas to produce CO2 and H2O. Hydrocarbon, here's an example of a hydrocarbon. It's got carbon and hydrogen in the molecule. That's one that we would be able to name, methane. Methane, our prefix tells me I've got 1 carbon there. Methane reacts with oxygen gas to form CO2 and H2O. When it comes to combustion reactions, they're all going to take the same form. They will all include a hydrocarbon and oxygen gas as reactants. They will all have CO2 gas and H2O as a product. So as far as typical equations, here's some suggested problems. These are ones that I think would be helpful for you to work on, and we could compare answers next time. Propane is involved in a combustion reaction. Write a balanced equation and determine the total number of molecules of product for every 1 molecule of propane that reacts. So in order to answer that, you need to say, okay, what is the formula for propane? What is it reacting with? It's going to be oxygen gas. What will be the products? Okay, now let me balance that. Really good application problem. Here would be another one. Hexane is involved in a combustion reaction. If 6 molecules of hexane were used, how much oxygen gas would be required? Hexane, you have to begin by being able to write the formula. It's a combustion reaction. So it's combining with oxygen gas to give me CO2 and H2O. I need to balance that. Now I need to use that as a recipe. If I have 6 molecules of hexane, how much oxygen gas would go with it? Really good application problems here. And notice they involve both naming and recognizing what a combustion reaction is. These would be really good ones for you to try to see if you could do. On the same topic, this is one very similar. Methanol reacts with oxygen gas to produce carbon dioxide and H2O. That really sounds like a combustion reaction. Here's a few different questions about the balanced equation. How many molecules of carbon dioxide are produced for every molecule of methanol? What if you produce 10 molecules of CO2? How much H2O would also be produced? Or if you start with 6 molecules of methanol and 6 molecules of oxygen gas, what's in the container after it fully reacts? Extra bonus, what would this look like at the particle level? These are all really good examples for you to try once again. I'm trying to bring together some really comprehensive questions that begin with aspects of naming. Can you write a balanced equation? And then can you begin to interpret it? Really important, I think, and it would be really valuable if you're able to try the questions that I have here on the slide. We can compare some of these within our next class. I give some example problems or end of chapter problems as far as balancing chemical equations using word descriptions. For a couple of these, like in 315b, it says potassium chlorate, that's the formula for it. Hydrogen sulfide gas, that's the formula for it. So as far as balancing equations and using from a word description, here's some end of chapter ones that I think are right on the mark if you want to practice it. Our last topic that we're going to move on to within class here is looking at Avogadro's number and how that relates to the idea like the mole. I want to give you a mental break on this though, okay? I've got right now 7:23. Um, let's meet back at 7:30, okay? You can either hang out here, stretch, lay on the floor, I don't know. Let's meet back here in 7 minutes, okay? If you got questions and you want to ask within the chat or talk with me, I can try to work on it. But let's give ourselves a mental break so we can do a good job with Avogadro's number to finish class. Okay, a couple comments here coming in the chat. It's the cat's name Ian. I did not get that when I saw it in the chat showing up initially. It is not cat Ian. That would be clever. I'm not sure my wife would allow that. Cat's name is Rosie. She might make an appearance here before the night's out. Uh, as far as required memorization, I would say that the key aspect of the naming, I would look back to chapter 2. I would be looking at the figure within chapter 2 that lists the cations in bold and the anions in bold. The anions in bold include quite a few examples of polyatomic anions. So being able to memorize the cations and the anions, that would be one thing. As far as other ones related to that, the acids that I mentioned tonight, these common ones, add those to another thing that you'd be seeking to memorize. Uh, Jasmine, no, I would say that when I'm looking at that, um, whether I'm looking at hydrogen gas, hydrogen as a solid, hydrogen as a liquid, in all of those cases, I'm still preserving the hydrogen molecule. But what I'm pointing out is a lot of times people get hung up, well, when is it an atom? When is it a molecule? When it's in its elemental form, then it is a diatomic molecule. And when it comes to things like hydrogen gas, oxygen gas, nitrogen gas, when we encounter those in our everyday world, they're as gases. And so that's why I'm saying think about those under those conditions to be diatomic. You're absolutely correct, though. If I said, what does solid hydrogen look like? I think it would be H2 molecules as the solid. But I think that you'll typically be finding it in questions where it'll be discussing things like hydrogen gas, and that's what we want to be alert for, to think about them as molecules. Okay, so I got 7:30. Let's see if we can finish strong here. So if I look at where we are going within chapter 3, at the start with balancing chemical equations, I think crucial within that is understanding what information do we have with our coefficients, And what do we have with our subscripts? And the coefficients are being used to tell us our simplest recipe that we have that tells me the proportions of how the reactants combine to form the products. When I'm looking at the chemical reactions, key one within that is understanding what is included in a combustion reaction. And I was trying to give a couple examples where that was linked back to aspects of naming that we saw within chapter 2. Now, when we move on to the idea of Avogadro's number, we're going to be looking at relationships between what's called the mole, the mass, and the number of particles. This one is going to be more numerical based than the other ones, but we're going to use these ideas in subsequent parts of chapter 3. So within this part, I've got really a total of 4 different learning objectives. We've already done 2 of them. We've already looked at balancing chemical equations, and we've looked at combustion reactions. The idea of combination or decomposition reactions, those are other reaction types within the chapter. I think if you glance at those, you're going to be able to understand those. The reason I emphasize combination ones is that's the most specific one that I need you to understand. These next 2 parts, in 3.3 and 3.4, we're going to be doing some calculations. We'll be doing some math. First part is calculating the formula weight. This was a question that I had in Perusal and people did a really good job with. So I gave the formula here, Fe2O3. That's a common name for rust. What would be the name of it? What would be the formula weight? And how much of that is coming from the iron? So within this one, when I'm saying what's the name of it and the formula weight and the like, I would definitely be looking at the periodic table for this because I've got to look up information. I would be naming this iron 3 oxide. Iron, if you recall, can either be +2 or +3. Oxygen is 2-, so it must be iron +3 within that. People did a really good job answering that. When I'm looking at the formula weight for this, I'm looking to see that I have 2 iron atoms and 3 oxygen atoms. If I look at the values on the periodic table, these would be the mass values. Remember, those are the weighted average mass values once we account for the isotopic abundance. This would be then the total mass when I'm looking at Fe2O3. I could then consider what percentage of that is coming from the iron, and I get to about 70% of it is coming from the iron. Now, as I look at this one, being able to name it, once again, ideas of naming from chapter 2, they're not going to be just restricted to chapter 2. Those ideas are going to show up again and again, so we got to get comfortable with the naming. This idea of calculating the formula weight or talking about the percent of the total mass, those are new skills that we're going to be using for sure. In particular, looking at the periodic table to determine the weight of something, crucial skill for us. Now, if I look at this one, the units here are in AMU. AMU are called atomic mass units. I sort of skipped past that idea when we were looking back here in chapter 2. When we're looking at this, where we're talking about the total mass being 12 and the like, well, 12 what? When I talk about the charge, remember the smallest amount of charge that we have is 1.602 times 10 to the minus 19 coulombs. You don't need to know that specific value, but if you recall, that was what Robert Millikan found as the smallest step size that he would have in his oil drop experiment to explain the total amount of charge that was on different drops. So when I see +1 or -1, it's referring to different amounts in that increment. If I look closely over here for the mass is listed in AMU. The atomic mass unit, or AMU, that's the mass that we would use when we're looking at individual protons, neutrons, maybe an atom, a specific molecule. But you know, it must be a really, really, really small amount because a proton weighs almost nothing, right? So this atomic mass unit must be a really small amount. And in fact, the actual specific value, how many grams is it? We don't really use that information. We instead are going to be talking about the mass and get it into a scale that we can use. And by scale that we can use, we're going to be using the metric system and expressing the mass in grams all of the time. Crucial to that is this idea of Avogadro's number. This is what happens. So if you have just a single molecule of H2O, you would have an oxygen atom, another hydrogen atom, another hydrogen atom. You could add up the masses for those. So hydrogen's mass is really close to 1. Oxygen's mass is really close to 16. 16 plus 1 gets me to 18. If I'm adding up the masses for those individual atoms, then my units are what are called atomic mass units. That's going to be a really small amount. What if I, though, now, instead of talking about just one of those molecules, I scale it up by talking about it by a whole mess of them. And by a whole mess, that's a scientific term for Avogadro's number, 6.02 times 10 to the 23rd. Instead of just talking about one molecule, let's talk about 6.02 times 10 to the 23rd of those, or a mole amount. In that case, instead of having my units be AMU, now my units are grams. And instead of talking about the mass of one molecule, we're talking about the mass for a mole of them, the molar mass. We're going to be using molar mass all the time in this class. This table from the book shows you could think about the mass of a single atom, but if you have a mole's worth, then that mass is in grams. Same thing if you're talking about a molecule. You could have the mass of a single molecule, but if you have a mole's worth, now that mass value is in grams. It works if you're talking about an element like silver. It works if you're talking about an ionic compound. We're going to be using the values on the periodic table as gram amounts all of the time because we're going to be considering mole amounts almost all of the time as well. The conversions that we could make back and forth between grams, moles, and the formula units are shown here. The idea here is that we can go back and forth between grams and moles by using the molar mass, the value that would be listed on the periodic table. This right here of going back and forth between the number of grams and the number of moles, or the number of moles and therefore how many grams it is by using what's on the periodic table, absolutely essential skill for us. Now, if we wanted to think about, well, how many particles do I actually have there? How many atoms are actually there? Well, then we would use our scaling factor of Avogadro's number. That's not really something that we ask very often. We're really going to be frequently going between grams and moles. Occasionally, we might say, well, how many actual particles are there? But our more common skill will be using the molar mass. Let me show you a couple examples here. So these are ones that were in the pre-class slides, but I want to illustrate a couple points. So this first one right here, MOL, that's the symbol for moles. You have 0.00105 moles of something called cholesterol, and it has a mass of 0.406 grams. What would be its molar mass? I come back to saying, well, let me define what molar mass is. Molar mass is grams per mole. That's what I'm trying to find. Molar mass is grams per mole. The equation right here includes a gram term and a mole term. If I look at the question, it tells me a certain number of grams. It tells me a certain number of moles. So I can just calculate that proportion. And I find that it has a molar mass of 387 grams per mole. I'm going to put this first question in the category of, okay, I've got 2 out of 3. 2 out of 3 meaning molar mass, grams, and moles. If you tell me grams and moles, I can get to molar mass. If you tell me molar mass and moles, I can get to grams. If you tell me molar mass and grams, I can get to moles. My point is, if you've got 2 out of 3, you can solve for the missing one. Many, many times we have questions where that's the point. You got 2 out of 3 things, solve for the missing ones. This question, what is the molar mass? Once you write the definition of molar mass, I think it becomes apparent that you have 2 out of 3 and you can solve for the missing one. Now this next one right here, it's more complex than just 2 out of 3. It says a sample of ethanol, and it gives the formula there, includes a certain amount of carbon. How many hydrogen atoms are in this? This is not a simple, you've got 2 out of 3. This is an example involving dimensional analysis. So I'm going to start out with what I know, how many grams of ethanol I have, grams of carbon in the ethanol sample. And I want to finish with how many hydrogen atoms. And in this case, I've got quite a few conversions that I need to do along the way. One strategy here, if you're doing dimensional analysis, if you start with what you know and you put down where you need to finish up, notice then the rest of the canceling always has to be numerator to denominator, numerator to denominator. So if I start out by saying I have a certain number of grams of carbon in the ethanol sample, I've got grams of carbon, grams of carbon. What else might I know about grams of carbon? Okay, I know that 1 mole of it is 12 grams. I get that by looking at the periodic table. How do I now cancel 12 moles of carbon atoms? There's 1 mole of carbon for every 1 mole of carbon atoms with 12 grams. Then I see that I have 2 moles of carbon within the ethanol's formula. Then I can see what does it mean to go from moles of hydrogen that were in that formula to how many atoms that I have. So what I'm trying to do is sort of conceptualize what does it mean to talk through a dimensional analysis that would start out with grams of carbon in the sample to get me to hydrogen atoms. I figured out from the grams to how many moles of carbon to moles of hydrogen to atoms of hydrogen. There's not like one set scheme that you always have to go through, but I think with a little practice within this, you can see how the dimensional analysis comes together. I'm going to call this a learning objective from this section. To me, this is an exam question involving an application of Avogadro's number. I think on your first exam, I think you're definitely going to have a question involving that. The second example right here, where you have to use dimensional analysis, very typical one. So I want to give you some examples so you can begin to practice that and see how this idea comes together for you. So in the pre-class video, at the very end of it, I shared a couple examples. Both of these are in that category of being able to look at the formula, think about how many atoms were present, and look at the various relationships. If you want to share ideas with me on these questions, I'll be very happy to. So these would be ones to begin to practice where you're applying Avogadro's number with dimensional analysis. But I want to give you a little bit more of a resource than just those questions. I want to guide you to some information within chapter 3. So within chapter 3, what you're going to find now, we have more numeric questions, more numerical ones that you're going to be doing calculations for. Chapter 3 now has many examples of sample exercises where they work through very typical questions and they show you how to solve it. So one thing that I want to direct your attention to, please look at the e-text for chapter 3. There are probably 8 or 9 different sample exercises where it allows you to work through and see the problem. Paired with those, right after those, they have these different self-assessment questions where you can submit your answers right in here and it tells you if you're right or not. So my point is that they've added some really nice resources in chapter 3 that will guide you through different calculations. They'll give you suggestions. They'll allow you to practice it. Using the e-text for chapter 3, really important, because so many of these, when it comes to practicing and working with the different numbers and the calculations, you need to get feedback. You need to determine, hey, am I doing this right? What would be an appropriate strategy? So if you have not really used the e-text much for chapter 1 or 2, I think you can probably get by with that. But in chapter 3, absolutely, please check it out as a resource as far as being able to see the different sample exercises. If you look within chapter 3 at the end, 2 different sets of calculations that we're talking about. We talked about being able to calculate the formula weight given the name of a compound. That's exactly what's going on here. You see different formulas written. Sometimes it's the formula, sometimes it's the name of it. Can you use this to then look at the periodic table to come up with the formula weight? Really good examples. 3.26, now this is looking at the percentage. This would be ones where you have the formula, you're looking at the periodic table, you're doing the calculation. Really good examples here to practice. On this one, when it comes to Avogadro's number in the mole, all of these are great examples. All of these are great examples to see, can you set up the appropriate dimensional analysis to solve for the appropriate value that they're looking at. And I want to double back as far as when I'm giving you examples or things to look at. If you recall back on this slide right here, I pointed out both sets of these as good ones for you to work on. Now, if it seems like we're finishing up class and my main point is, hey, there are resources in the e-text to look at when it comes to calculations. There are good representative problems for you to begin to practice. And those practice problems include the ones that I know you're going to have to work on in order to master. And that we can have these other suggested problems for you to work on. If it sure seems like I'm giving you a to-do list, well, I have to, okay? There's no other way that I can, I can get in your head and somehow learn it for you. I know that the things that we're coming to within chapter 3 really benefit from working through the numbers. Even though I've worked on these problems myself for decades, I get better when I work on them in chapter 3. I get better setting up the problems, writing the balanced equations, doing the calculation, looking at the periodic table. And I'm someone who's done it literally for decades, but my proficiency increases. So my point is, with a little practice within here, your proficiency is going to increase as well. So I'd like to leave you within that. What we're going to do next time is we're going to pick up and we'll work more within chapter 3. Look for the videos that I'm posting within perusal on this content, and I'll send you an update as far as the extra credit one that I mentioned, as far as what I think are very important learning strategies that are going to help you out. I'll hang around if you got questions. Once again, I really appreciate your attention.